that's one of the big concerns that we have every year, but especially this year, given how dry it's been, is the increasing threat of wildfires.
A multi-billion-dollar restoration plan was passed by Congress in 2000 and includes dozens of infrastructure projects across Florida.
January, South Florida. The air tastes of smoke, the marshes are being drained, and what was once hidden beneath 16,000 acres of wetlands is suddenly exposed. Holes pock the mud like a battlefield scarred by creatures no one expected. Armored catfish, invasive pythons, and something even stranger moving beneath the receding water. This isn't just wildlife. It's a secret ecosystem that has been quietly evolving, breeding, and surviving under the surface for years, hidden from scientists and regulators alike. When humans alter the water, the swamp pushes back, and what it reveals challenges everything we thought we knew about life, invasion, and survival in the Everglades. What lives beneath the drained waters? And can the ecosystem survive the truth? Beneath drained waters. To understand what the drawdown revealed, you need to understand the landscape it happened in. Stormwater treatment area.
Known as stormwater treatment areas, STAs are constructed wetlands, the largest in the world, designed to remove phosphorus from the water as it flows south through the Everglades and into Florida Bay.
One West, STA-1W in the bureaucratic shorthand of the South Florida Water Management District, is part of a network of constructed wetlands that sit along the northern edge of the Everglades, south of Lake Okeechobee and the vast Everglades agricultural area. These aren't natural marshes. They're engineered systems, built specifically to filter phosphorus-laden runoff from sugarcane and vegetable farms before it enters the remnant Everglades. Water flows through shallow marshes planted with cattails and submerged vegetation, which absorb nutrients, and the treated water continues south. The system is, in concept, an elegant solution, using nature's own filtration mechanisms to clean what industry has dirtied. But the STAs require maintenance. Levees need inspection, vegetation needs management, sediment needs assessment, and to do any of that, you have to periodically remove the water. When the pumps started and the water level began to fall, the first signs of trouble were ordinary. Fish, largemouth bass, bluegill, various sunfish, crowded into shrinking pools, their dorsal fins breaking the surface like grass blades in a puddle. Wading birds descended in enormous numbers, picking off the concentrated prey. Alligators converged on the last remaining deep spots, stacking into dense aggregations that looked almost staged. Dozens of animals in water barely deep enough to submerge them. This is what a dry season looks like in the Everglades, accelerated. The water compresses, life concentrates, the weak die, the strong eat. It's brutal, but it's natural, or at least, and it mimics a natural process. But the canal banks told a different story. As the waterline retreated, what had been invisible became grotesquely visible. The earthen levees, the same levees designed to hold and direct millions of gallons of stormwater, were riddled with burrows.
Returning the Everglades to its natural habitat, construction includes over 3.2 million cubic yards of excavation and over 1.8 million cubic yards of embankment to create the canals and levees that make up the STA.
Not scattered holes, systematic excavations. In some stretches, crews documented more than 400 burrow openings in 200 meters of bank. The soil between them was undermined, honeycombed, and structurally compromised. In places, the bank was so perforated that it crumbled under the weight of a person stepping on it. The surface intact, but the substrate hollowed out beneath. The smell that rose from the exposed banks was dense and specific, a combination of anaerobic mud, decaying organic material, and something else, something acrid and fishy. The crews working the drawdown described it as overwhelming in the morning hours before the sun baked the surface. What had dug these burrows? The answer was literally staring back at them from the shallow water. Armored catfish, Loricariidae, hundreds of them, clustered in the remaining pools, their flat, plated bodies stacked on the bottom like tiles. Some were wedged into burrow openings, half in and half out of the mud, breathing air. Because that's what these fish do. They breathe air. They survive out of water for up to 20 hours. And they dig. But the catfish burrows were only the surface layer of what the drawdown exposed. As crews moved deeper into the system, clearing canals and inspecting structures, they encountered something that transformed a routine maintenance operation into something closer to an ecological crime scene. The canals weren't just sheltering fish. They were sheltering predators. Catfish conspiracy. The armored catfish, known colloquially as plecos, short for plecostomus.
The armored catfish are an aquarium release fish. This is one of the rivers in Texas that has been invaded by suckermouth armored catfish.
The suckermouth catfish genus most aquarium hobbyists would recognize are native to Central and South America. They arrived in Florida the way most of the state's invasive species arrive, as pets. Sold in aquarium shops as algae eaters, they were purchased by the millions over the past 4 decades. When they outgrew their tanks, or when owners tired of them, they were dumped into canals, retention ponds, and drainage ditches across South Florida. That was a mistake of almost incomprehensible ecological proportions. Because the armored catfish is not a passive aquarium janitor. It is an engineering organism. The males dig burrows, deep, or lateral excavations into canal banks and shorelines to attract females for spawning. Each burrow extends 18 inches to 2 feet into the substrate. The female deposits her eggs inside, the male guards them, and the cycle repeats. A single male may excavate multiple burrows per breeding season. Multiply that by a population numbering in the millions across South Florida's waterways, and the math becomes structural. The Florida Fish and Wildlife Conservation Commission has described the impact plainly. The fish destabilize banks and contribute to erosion and increased turbidity. But that clinical language understates what crews found during the drawdown. In the stormwater treatment areas, the catfish hadn't just made holes. They had turned the levee infrastructure into something resembling a termite-eaten beam, superficially solid, fundamentally hollowed. The burrows are interconnected. Water seeped through them. The earthworks designed to hold and direct millions of gallons of agricultural runoff were being undermined from the inside by a fish that was originally bred to clean aquarium glass. The catfish also survive in conditions that would kill most freshwater fish. Their modified intestines allow them to absorb atmospheric oxygen. They can reffle, a unique form of terrestrial locomotion where the fish flings its armored tail to one side and drags itself forward using its mouth as an anchor to reach new water bodies when their current habitat dries. Their bony plates make them nearly impervious to predation by herons, ospreys, and other native fish eaters. Birds that catch them often give up trying to penetrate the armor and simply drop them. Those dropped fish, still alive, reffle to the nearest water and resume breeding. Captain Blair Wiggins, a veteran Florida fisherman, put it in terms that capture the problem's invisibility. When you get water-invasive species like these guys, they're out of sight, out of mind. You don't really see the destruction. That invisibility is the core of the problem. Python hunters can at least walk the levees looking for snakes. The catfish damage happens underwater, inside the earth, in structures you can't see until you drain them. The stormwater treatment area drawdown didn't reveal a new problem. It revealed a problem that had been compounding, unseen, for years. But the catfish burrows were small. What crews found deeper in the canal system was not. Python cities. Picayune Strand State Forest sits in Collier County, southwest Florida, in between Naples and the western boundary of the Everglades. It's part of a massive restoration project, one of the largest wetland restoration efforts in North American history, aimed at reversing decades of failed drainage and development. The land was originally drained in the 1960s for a subdivision called Southern Golden Gate Estates that never materialized, leaving behind a grid of canals and raised roads cutting through cypress swamp and pine flatwoods. When restoration crews began plugging canals and removing roads to re-establish the natural sheet flow of water through the strand, they encountered something in the canal infrastructure that nobody had modeled. The canal banks had large burrow openings, not catfish-sized, much larger, wide enough to accommodate an animal with a body diameter approaching the circumference of a telephone pole. They were python dens. Burmese pythons, Python bivitatus, are Southeast Asia's native constrictor. They arrived in the Everglades through the pet trade, with a major population boost likely following Hurricane Andrew in 1992, which destroyed a python breeding facility near the park boundary and released an unknown number of snakes into the surrounding swamps. Since then, they have become what the U.S. Geological Survey describes as one of the most concerning invasive species in the region. The numbers are difficult to comprehend. Population estimates range from 30,000 to more than 300,000 animals. They grow to over 18 feet. They lay an average of 49 eggs per clutch. Yet they consume 37 documented species of native wildlife, from songbirds to white-tailed deer to 6-foot American alligators, and they are nearly invisible. One study found that experienced herpetologists had only a 1% detection rate when searching for pythons in semi-natural environments. What the canal clearing in Picayune Strand revealed was the reason for that invisibility. The pythons weren't on the surface. They were underground. Crews found multi-chamber burrow systems, not simple hiding spots, but complex underground dens with separate entrance and exit tunnels, widened interior chambers, and evidence of long-term habitation. The pythons were using gopher tortoise burrows, mammal dens, and self-excavated tunnels in the soft limestone substrate to create permanent subterranean colonies. And during cold snaps, which can drop South Florida temperatures below the python's metabolic threshold, the snakes retreat underground and enter brumation, a reptilian dormancy that allows them to survive conditions that would otherwise kill them. Temperature loggers placed in brooding nests showed that females use shivering thermogenesis, rhythmic muscle contractions that generate heat, to keep their eggs alive underground, a behavior never previously documented in this species. The ecological impact of these underground colonies has been devastating. Road surveys comparing mammal populations before and after python proliferation documented declines of 99.3% for raccoons, 98.9% for opossums, 87.5% for bobcats, and effectively 100% for marsh rabbits, cottontail rabbits, and foxes. In one study, researchers fitted marsh rabbits with radio transmitters and released them into Everglades National Park. Pythons killed 77% of them. The reintroduced rabbit population was extirpated in less than 11 months. For years, researchers had been hunting these snakes on the surface, walking levees, driving roads at night, using scout snakes, fitted with radio transmitters to locate breeding aggregations. The canal drawdowns and restoration clearing revealed that this approach was, in a sense, searching the attic while the problem lived in the basement. Entire colonies were thriving underground, reproducing, sheltering from cold, and emerging to hunt in an ecosystem they had already functionally emptied of medium-sized mammals. The phrase underground python cities is not a metaphor. It is an architectural description. Multi-entrance, multi-chamber, temperature-regulated subterranean habitats occupied by the most successful invasive predator in North American history. The scale of the removal effort hints at the scale of the problem. A single contracted python hunter removed 87 pythons in a single month in 2025, including a 14-footer found crossing a road near Naples, plus 3 nests. That hunter's program areas span from the Loxahatchee National Wildlife Refuge to the stormwater treatment areas to Big Cypress National Preserve to Picayune Strand, essentially the entire western Everglades corridor. Since the formal removal programs began, more than 4,000 pythons have been taken from the wild. Experts acknowledge this is likely a small fraction of the total population. And every female removed, each capable of laying 50 to 100 eggs per year, is described as a step in the right direction, language that speaks less to confidence than to the grinding mathematics of trying to outpace exponential reproduction. The deeper discovery, the one the canal clearings made possible, is that the pythons have fundamentally restructured the food web. The collapse of medium-sized mammal populations has cascaded downward. Fewer raccoons and opossums means fewer nest predators for ground-nesting birds, which initially sounds positive until you realize that the same missing mammals were prey for native predators like bobcats, coyotes, and raptors. The entire trophic structure is being rearranged around the absence of animals that used to be common. And while the visible invasions played out above ground, something else was happening in the water itself. Predator pit collapse. In the spring of 2025, Marshall Jones stood in a sawgrass field west of Broward County and tried to explain what he was seeing to a CBS News crew. Jones is a fifth-generation Gladesman. His family has lived on the edge of the Everglades for over a century. He runs Max Fish Camp, 7 airboats, daily tours, a livelihood built on water. But on this day, there was no water. The ground beneath his boots was dry and cracked. Canals that normally ran thigh-deep were ribbons of mud. His airboat business was shut down. And all around him, the Everglades was collapsing into itself. This particular drought is coming on earlier and with a harder, more rapid onset than I've ever seen, Jones said. And the South Florida Water Management District confirmed the numbers. Rainfall was down 50% since November. 84% of the state was classified as moderate, severe, or extreme drought, conditions not seen since 2012. The U.S. Drought Monitor labeled most of the Everglades as extreme. Meteorologist Matt Devitt described it as the worst locally in 24 years. What that meant ecologically was a predator pit at landscape scale. A predator pit is what happens when shrinking water forces prey and predator into the same diminishing space. In normal conditions, alligators disperse across millions of acres of shallow marsh, spread thin enough that the ecosystem sustains them. But when the water disappears, when a wetland 60 miles wide contracts into scattered puddles and man-made canal segments, everything converges. The alligators don't leave, they concentrate, and they bring their appetites with them. Along the Loop Road in Big Cypress National Preserve, field biologists documented the progression in real time during May 2025. Locations that had held several feet of water during previous years were bone dry. Small muddy puddles, some no larger than a living room, contained clusters of armored catfish, packed together and breathing atmospheric air. Other pools held alligators, motionless, waiting. At the Oasis Visitor Center boardwalk, a deep canal section became a compression chamber of predation. Gators stacked on gators, gar thrashing in the shallows, and one recognizable alligator with a damaged lower jaw photographed eating a gar in the same spot it had occupied 3 years earlier. The water level comparison photographs between 2022 and 2025 were staggering. Same location, same angle, half the water gone. The birds came next. Wading birds, great blue herons, wood storks, white ibises, great egrets descended on the concentrated pools in enormous numbers. They came early, months ahead of their normal dry season schedule, because the drought had accelerated the timeline. At Shark Valley, the 15-mile tram trail that runs through the heart of Everglades National Park alongside the Shark River Slough, Visitors in January 2025 counted dozens of alligators basking on both sides of the paved path, some with body parts extending onto the trail itself. Birds lined the canal edges shoulder to shoulder. In November 2024, a video went viral. A massive alligator walking through Shark Valley with a dead Burmese python clenched in its jaws, witnessed by stunned visitors at the observation tower. The Everglades was eating itself, and tourists were watching from bicycle seats. But the spectacle masked a quieter catastrophe. As hundreds of large-bodied animals crowded into stagnant pools, dissolved oxygen collapsed. Algae blooms, fueled by nutrient-loaded water with nowhere to flow, consumed what oxygen remained. Jones described it plainly. The fish in the water just don't have enough oxygen to survive. That's why you see the water with this green color, nutrient loading. An algae is consuming all the oxygen in the water, and that's causing the fish to die. The result was mass mortality, not from teeth or talons, but from suffocation. Fish floated belly up in thick mats along the canal banks. The stench reached the highway. And this is where the predator pit reveals a deeper dysfunction, one that's entirely human-made. Historically, the Everglades dry season was a slow, gradual recession. Water retreated across a landscape 60 miles wide, giving aquatic organisms time to redistribute, to follow the moisture south, to disperse into alligator holes that served as natural refugia. The canal and levee system built through the 20th century,
Canal levee, and Lake Bourne flooded over the second levee, protecting St. Bernard.
replaced that gradual recession with engineered discontinuities. Water doesn't slowly retreat across a 100-mile sheet anymore. It drops through pump stations and control gates, creating abrupt edges, pools that go dry in days, while canals a few hundred meters away remain full. The ecological consequence is that fish and invertebrates get pulled into artificial canal habitat during dry periods, concentrating prey in a way that feeds predators but strips the surrounding marsh of the forage base that wading bird colonies need to raise chicks. Hardin Waddell, a research ecologist with the U.S. Geological Survey who has studied Everglades alligators for years, summarized it with a phrase that functions as both scientific finding and warning. The hydrology matters for alligators, and extreme dry events can reduce the populations. The predator pits were dramatic and visible. They made for extraordinary footage, but they were symptoms of something the cameras couldn't capture. A water system designed for agriculture and flood control, not for the 2,000 animal and plant species that depend on timing, depth, and flow that no pump station can replicate. By February 2026, the pattern was repeating. Local 10 News reported the Everglades going dry again, wildlife flocking to shrinking pools, the same overcrowding, the same green water, the same fish kills. Jones was back on camera, watching alligators trudge through mud where water used to be. While the visible chaos unfolded above the surface, something invisible was leaching from the sediment below. Poison in the sediment. The stormwater treatment areas exist for a single purpose: to strip phosphorus from agricultural runoff.
Well, today construction begins on the Cochrane Basin Stormwater Treatment Facility. That water filtration project will not only impact the treatment facility, but also recreation in the area.
And they work. Cattails, periphyton mats, and submerged vegetation absorb phosphorus from the water column and incorporate it into their tissues. When these plants die and settle to the bottom, the phosphorus gets locked into the sediment, buried theoretically in an organic layer that accumulates over years and decades. The system functions beautifully as long as the sediment stays wet. When it dries, the chemistry reverses. Exposure to air oxidizes the organic material in the sediment, breaking down the biological matrix that was holding the phosphorus in place. The phosphorus doesn't disappear. It transforms from a stable bound form into a reactive soluble form that will flush back into the water column the moment the system is reflooded. Years of accumulated nutrient capture can be undone in a single drawdown cycle, and phosphorus is only part of the equation. The sediment in South Florida's managed wetlands also contains elevated levels of sulfur, mercury compounds, and the residues of agricultural pesticides, including atrazine and endosulfan. When these sediments dry and then re-wet, they undergo chemical transformations that can increase the bioavailability of mercury, meaning more mercury enters the food chain, moving from sediment to microorganisms to fish to wading birds to apex predators like the Florida panther. Then there's the biological payload. When phosphorus-enriched water re-enters the Everglades system, it fuels the growth of cyanobacteria, blue-green algae, which can produce toxins dangerous to both wildlife and humans. Florida has experienced repeated toxic algae blooms in recent years, and then the linkage between agricultural phosphorus loading and bloom intensity is well documented. The stormwater treatment areas are designed to prevent this, but if the sediment releases its stored phosphorus during maintenance drawdowns, the treatment system becomes, temporarily, a source of the very pollution it was built to control. There is also a less publicized but deeply concerning biological threat embedded in the Everglades food web, the rat lungworm parasite. Angiostrongylis cantonensis, a parasitic nematode that can cause eosinophilic meningitis in humans, has been documented in South Florida's invasive species, particularly in the island apple snail, another non-native organism that has colonized the Everglades. The parasite cycles through rats and snails, and humans can be infected by accidentally consuming contaminated water or undercooked snails. As the Everglades food web becomes increasingly dominated by invasive species, the pathways for parasitic transmission grow more complex and less predictable. The poison in the sediment is not dramatic the way a python colony is dramatic. It doesn't make for a compelling video, but it may be the most consequential finding of the drawdowns, a slow-motion chemical reckoning that reveals the fundamental tension at the heart of Everglades management. The systems built to filter pollution are themselves accumulating pollution, and every time we look underneath them, we find more. Beneath the drained wetlands, the Everglades has been quietly waiting, seeds buried for decades, crayfish burrowing, native plants ready to reclaim the marsh, and the invasives, the catfish, the pythons, all symptoms of human decisions, of water diverted, schedules imposed, ecosystems disrupted. We've seen the damage, but we've also glimpsed the resilience. The question now isn't whether the Everglades can survive. It's whether we will act before the next drawdown, the next disruption, the next tipping point. Or if we'll let one of the planet's most extraordinary wetlands become a cautionary tale of what happens when water runs out and time runs shorter than we realize.